Great, thanks a lot. Yeah, thank you for the introduction. Yeah, I know Bryony well because we were overlapping with our PhDs. And yeah, rightly said, I've kind of moved on from the academic world into an industrial role for the time being. And yeah, although I'm still kind of working on space weather and solar physics related things, it's my sort of day-to-day mathematical work is very much statistics based now. So I thought I'd talk to you a bit about that. And bear with me, my PhD was definitely not in statistics, but there's probably people in this audience that know a lot more about this sort of stuff than me, but I should be able to give you a flavor of what we're doing in our research, why it's important, and yeah, maybe a little flavor of some of the mathematics that goes into it. Let me just shut this, there we go. Yeah, so I gave a talk yesterday about careers, so I kind of introduced myself a little bit then, but maybe I could do something like that, but smaller now. So yeah, I'm working for EDF, which is one of the biggest energy companies in the UK. It's a French company. I've worked there for about a year, and I'm in the R&D department. There's a variety of us working on all sorts of stuff, from kind of nuclear energy related R&D, like optimizing graphite rods and that kind of stuff, all the way to us who are on the safety side, basically trying to make sure that our power stations remain safe for many years and decades to come, especially in a changing climate and a sort of modern day world. So yeah, I'll talk a little bit about the context of my job. So yeah, the nuclear energy industry and natural hazards within that. And then talk a bit about extreme value analysis, which is one of the main statistical approaches that we use in our work. And then I'll do a little bit of an application of that to space weather data, which is my forte. So yeah, nuclear energy, I think, is quite an important part of the UK's energy generation, and the same for elsewhere across the world. But this is kind of a bit of a flavour of what we currently do in the UK regarding nuclear energy generation. So this is the amount of carbon that's produced when we generate electricity in the UK, and you can basically see it's been pretty high and is generally dropping due to the commitments that the government have made towards a one target, which is a 2030 target of carbon intensity per kilowatt hour. And yeah, kind of on the way there, I guess, but there's a lot further to go. Yeah, so you can see on the pie chart here, we've got, I think this was a day back in April that I just chose at random, the sort of mix of energy generation from the UK, and we have nuclear, the slice here, yeah, between sort of 10 and 15%. But across the world, the mix of energy generation is quite different. So that there's some countries that have no nuclear energy at all. There's some countries that have a nuclear making up the vast majority of their energy production. So, for example, on the extreme end of things, France is proportionally the world's biggest generator of nuclear energy. And EDF is a French company, so we kind of have a big input with the nuclear power stations in France as well as in the UK. So in France, nuclear energy makes up about 85% of their energy budget. And then all the way down to UK is down here at between 10 and 15%, and America in total produce the most amount of nuclear energy, but as a proportion of the amount of energy that they produce altogether, it's much lower than France. So where does EDF fit into this? So yeah, it's a French company. There's like intertwined with the government in France. It's not a private company there, whereas it is private in the UK. And it basically runs manages all of the nuclear power stations that are running in France and in the UK, and has a variety of other kind of renewables and other energy generation assets around the world. There are, like, I think there's 2 fossil fuel plants that EDF own, both of which are closing very soon, which is good. So soon we'll be a completely kind of carbon negative company, which will be fantastic. And in the UK, we're EDF are in the process of developing two new nuclear power stations. One at Hinkley Point C, which you may have heard about in the news. In fact, the background picture on this page is the biggest crane in the world, called Big Carl. I think that's a fantastic name to name a crane, lowering in the top dome over one of the nuclear power station, the reactor for Hinkley Point C, the new nuclear power station. And then there's another one on the other side of the country in East Anglia, at a place called Sizewell, where there are already two reactors, and they're planning to build another one. So a lot of our work in the R&D department is to try and facilitate the development of these projects in order to make sure that they're safe in now and into the future. So yeah, these are where all the power stations are in the UK and France. So Hinkley Point is here and Sizewell is here. These are where the two new reactors are being built, but there's a variety of other ones across the UK and many across France. A lot of nuclear power stations tend to be by the coast. As you can see, all the ones in the UK are by the coast. A lot of them in France are as well. And this is by design. This is because seawater is a very cheap way of cooling down a nuclear power station. So these places often have big industrial water inlets that guzzle just millions of gallons of water per day in order to cool these systems down. So yeah, but being by the coast, these systems are kind of exposed to a particular type of hazard, more so than others. So especially in the UK, we have quite, let's say, active coastlines that change with geological changes and with meteorological impacts. So we have pretty ferocious weather here sometimes, and a lot of our work in R&D in EDF is to make sure that these nuclear power stations are resilient to the sort of worst cases that we can imagine around the UK and around France. And on an object level, this kind of looks like building the seawalls and things like that are an appropriate height to manage the risks. Yeah, I'll skip over this. This is a bit more detail about R&D and EDF, and yeah, move into some natural hazards things. So I'm in the natural hazards research team at EDF, and we work on protecting the nuclear power stations from all sorts of hazards. So all the way from on the coast, a variety of things, through to kind of river flooding, lightning, hailstorms, and for me in particular, I work a lot on space weather, which are it's the name given to a collection of hazards that come from outer space, and I'll tell you a bit more about those later. I'll skip over this, I think, as well, because I want to leave some time to get into the mathematics. I thought I'd include this though, because this is maybe puts into context the need for the sort of research that I'm part of. So this is a series of CCTV frames from the Fukushima Daiichi nuclear power station that was damaged in 2011, which I'm sure many of you will remember this. There was a big earthquake in Japan, or off the coast of Japan, that sent a large tidal wave into the Japanese coast, caused a lot of destruction across many areas of Japan, and was a really tragic event. But most kind of relevant to my role is that it actually damaged quite significantly one of the nuclear power stations in Japan. You can see here just the influx of the tsunami into the site. So I'm not sure exactly what each of these bits are, but you can see kind of the industrial systems that are surrounding the plant. Most of the systems tend to be built on stilts like this here. You can see here there's kind of a stilted system up here, and that is to protect them from these sorts of extreme events that we try and protect the systems from. But even though there were many safety systems put in place, this wave ended up overwhelming the seawall and causing some damage. There were no lives lost due to the power station damage, but it sort of put into perspective for EDF and other power station operators around the world that nature is a big deal. We need to put in a lot of time and effort into making sure that there is sufficient resilience to all that nature can throw at us. Great, so that was a bit of an intro. I'll quickly go into some of the statistics that we use as a tool to do this kind of natural hazard research. And one of the main tools that we use is called extreme value analysis. So extreme value analysis is basically a name given to a variety of statistical techniques and methods that are trying to model the behavior of the extremes of a data set or of a distribution, probability distribution, rather than the bulk. So many applications are interested in how the mean of the data set is behaving. But when you're considering the sort of worst that nature can throw at you, then you really need to know what the statistical behavior of the extremes are. And yeah, so for example, that the huge tsunami that infiltrated the Fukushima nuclear power station, that was obviously an extreme event that was and not predicted by those that were operating the nuclear power station. And I put these pictures in as well because this was a recent example of an extreme natural hazard in my life recently. So on Sunday, there was some quite severe flooding in London. I've recently just moved to London from Sheffield, and I was driving home from visiting a friend in Essex on the day that there was all of this flooding. So I had an unpleasant journey, shall we say, that took many times longer than it should have done because I was trying to get through roads that were half flooded. Thankfully, I was not any of these two cars, but I did have a lot of holdups. And in fact, this is inside one of the hospitals, I think this was, that was really severely flooded. Okay, so a bit of an intro to extreme value analysis. So we're basically interested in the statistical behavior of extremes. So you can sort of say that the extremes will be something like the maximum of a sequence of random variables that are independent and identically distributed. And let's call that MN. And then we're basically interested in finding things like this. So like what's the probability that some new observation will be greater than or equal to the maximum MN. And if we are assuming that the X1 to XNs are independently, are identical, are independent, then we can basically use basic probability to take us to this here, with basically a multiplication of all of the cumulative distribution functions of the X1 to XNs. And the problem with this is that we usually don't know what the cumulative distribution function F is. So instead we use a variety of asymptotic theorems and extremes of distributions, and skewness are. So these are kind of 4 different numbers or values that can kind of tell you something different about the shape of a probability distribution. And of course, we're all very familiar with these first two. So the mean, this is just the location of the center. So for a symmetrical distribution like this, it would be like any of these, it would be the very middle value here. To the variance, we're all quite familiar with that, I think, which is how spread the probability is around the center. The skewness, which is the next moment. And this is the lopsidedness of the distribution. So I don't have a picture of it here, but kind of how much it's kind of shifted, or almost like it's falling over one side or the other. And then the kurtosis, which is very relevant to our research, is the heaviness of the tails. So I've drawn a picture here of kind of 4 different values of kurtosis and what that would kind of look like in a probability distribution. all the way from very small kurtosis, which would have like basically none of the probability density is in the tails or the extremes of the distribution, all the way to which would be like your blue line and your green line, all the way to the black line, which has quite a lot of the density is in the tails, so on the left and right hand side. So you'd say that would have a high kurtosis. So one of the approaches that we use in extreme value analysis is called the block maxima approach, which is a way, basically a way through which you can identify the extremes of a data set. So it doesn't matter so much what this data is showing, but if let's say you have this blue data set, so each of these points is a data that's come from some unknown distribution, and you basically want to model that data so that you can make predictions or make extrapolations into values that would fall outside this range. And the block maximum approach is basically a way in which you can choose the extremes that are going to be modeled by the distribution that you're going to model them with. And it basically splits up the data into blocks. So you'd say, yeah, I mean, you can imagine this is like, say, through time, and then up here you'd have like some severity of some natural hazard. So it could be like wave height, for example. And then you basically say, we're going to designate blocks, and each block might be, say, a day long, or it could be a week long, or a year long. It really depends on the specific application that you're working on. And then you say, okay, I'm going to choose the very highest value within each of those blocks. So it would be like these starred values here would be the ones that you would select as your extremes that are going to be modeled by your distribution. So that's one way to do it. And this has some pros and cons, this method. The main pro, or the main advantage of this would be that you have a high chance of choosing independent extremes if you do this. So remember before where we had to assume that all the x1s up to xn were basically independent and identically distributed. This block maximum approach will help you guarantee that independence of the extremes. Basically because you're not choosing too many extremes that are really close together. So they're always going to be separated by a significant time, if that's your variable. So they're unlikely to be connected to the same event. Whereas if they were very close together, so let's say like this one and this one, these two peaks, well, they might have just been caused by the same underlying meteorological event, in which case they wouldn't be independent because they would be dependent on this kind of overlying meteorological event that's happening. But there's obviously trade-offs. So the disadvantages of this approach are that you can end up selecting only a small number of points. Of course, it depends on how big your block size is, but you're basically not choosing some extreme values that that could be modeled by the distribution that you're going to be using. So for example, here we've chosen to not use this guy, and this guy, even though they're very extreme, even more extreme than one of the extremes that was chosen, because we're trying to make sure that we're not choosing values that are dependent on each other. And then an additional kind of question that you need to kind of put some work into determining is what the block size should be, and this is very much dependent on what your aim is with the research that you're doing, and what the background of the hazard is. Like, is it seasonal? Is it a daily hazard that kind of changes on the order of a day? Like, you sort of need to know some of the characteristics of the hazard that you're looking at in order to determine what an appropriate block size would be. So there is another commonly used approach to choosing extremes, and that kind of relies, that relies on the idea of threshold exceedances. So rather than choosing certain blocks and then choosing one extreme in each block, instead you say, okay, we're going to choose a threshold above which we're going to say all of those values, all of those values from the data are going to be selected as our extremes. And you can sort of write this mathematically. We basically want to characterize this kind of probability. So, so above a certain threshold, what's the sort of probability as you get further away from that threshold, higher and higher and higher? What's the probability that your instantiation of your random variable is going to be above that? And you can basically work that out to be this guy, but just like before, we don't know what f is usually. This is the whole the whole point of doing statistical inference. So instead, we can asymptotically approximate the value of this for a sufficiently large threshold u. And then, so to do that, we kind of go back to our textbook, and there's people that have very long ago in the past have worked out asymptotic theorems that basically give you a form of a distribution that will match what you're interested in for threshold exceedances and for a high enough threshold. And the name for this distribution is the generalized Pareto distribution, and it looks something like this, depending on what the parameters are. And it basically has this kind of form. I won't go into all the maths here, but this is like the functional form of the distribution. So to put this into practice, into whatever data you have, you do what's called the threshold exceedances method, also known as the peaks over threshold method. And you're basically choosing extremes that are above a particular threshold. So here, I mean, it doesn't matter exactly what this data is, but you can imagine you've got time on the x-axis and maybe wave height or some other variable that you're interested in. And you basically want to look at what the very highest values are, what the biggest waves are, or what the highest sea level is, or what the fastest river flow was. There's a variety of parameters that you might be interested in, and this is basically a way to select the extremes that are going to be modeled by your generalized Pareto distribution. So you can sort of weigh up which approach to use between the threshold exceedances method and the block maxima approach, and it sort of really depends on the sort of optimization of the trade-off between choosing enough extremes. So the trade-off between choosing enough extremes versus making sure that the extremes are independent. So for the threshold exceedances approach, the main pro is that you end up with, or you can end up with a lot of extremes that could be missed by the block maxima approach. But the problem is that many of these extremes could be dependent on each other. So as it's currently sort of used here, there's been no thought gone into how close together the extremes that you've chosen are. So it could well be that like all of these cluster of extremes here could be to do with one meteorological event, for example, in which case they wouldn't necessarily be independent. Therefore, the modeling, the statistical model that you are applying to them would not be appropriate, because the whole point was that in order to derive the generalized Pareto distribution, you had to assume that they were independent and identically distributed. Which, if they're all dependent on the same meteorological system, then they wouldn't be as independent as you like them to be. And just like with the block maxima approach, where you had this choice of block size, in this approach you have a a choice to make about the threshold, and you kind of want it high enough such that your extremes or the values that you select are only the very extreme most values, but you don't want it too high that you've got very little data to fit your model to. So again, there's another trade-off here between between including all of the extremes or not including any values that are in the bulk of the data set, but also including enough values that you're going to have a good representative sample of extreme values that you can fit your distribution to. So the sort of aim of all of this, or at least in a lot of my work, is in order to fit your distribution to the data so that you can extrapolate to understand something about the expected values that are outside of the distribution. So one of the key kind of extrapolations that we like to do is to try and estimate the severity of an n-year event. So you could define an n-year event by the most severe event expected over the next n years. So if you imagine, let's say if you're interested in the amount of rainfall at a given site, and you have measurements every day of the amount of rainfall that has fallen on that site, then you can use a model to fit to the extremes of that data set and then extrapolate that model in order to find what the 10-year event would be, the 100-year event would be, the 1,000-year event would be. And these are basically based on your model, what you expect the highest rainfall would be in that 10 years or 100 years or 1,000 years. And this is quite a useful way of defining, or not defining, but characterizing the threats or the risk that is posed by this hazard or rainfall or whatever it is to whatever infrastructure that you're trying to protect. Because there's no point in just building to the highest that you've seen in the past. You kind of need to have some additional leeway or additional protection to your system in case there are events in the future that are just bigger than they've been in the past. So yeah, the fit distribution, which is usually either the generalized extreme value distribution or the generalized Pareto distribution, depending on which approach you've taken, can then be used to extrapolate a variety of n-year events. And you end up usually trying to come up with a plot that's kind of like this. So you can read this as like the x-axis is your return period. So this might be how many years into the future are you kind of considering. So this would be like your 1-year event, your 5-year event, your 10-year event, 50-year event, 500-year event. And then what this plot is showing is that for each of these n-year events, it's saying this is what the estimated severity of that event would be. So that's what this kind of thick black line would be. The dots would be your data that you've fit the model to. And then the dotted lines would be some confidence interval around that best estimate value. And then from this, you can basically read off and estimate what the sort of extreme events would be expected to be outside of the range of data that you have. Which is very key when you're dealing with trying to protect infrastructure that you want to be protected for, say, 100 years in the future or 1,000 years in the future, but you might only have data that goes 50 years into the past. So it's a useful way to extrapolate these statistical trends. Okay, so with the time that I have left, I'm going to chat a bit about space weather and an application of these extreme value analysis tools to a data set of space weather data. So yeah, I think I described yesterday a little bit about what space weather is, but I'll go through it a little bit again. so that we are kind of clear what the data is showing. So space weather is an umbrella term given to a variety of different effects that the sun has on the Earth. And they tend to be caused by solar events like solar flares and what's called coronal mass ejections, which are big balls of plasma that are fired out from the sun into space that can interact with the Earth's magnetic field if we're unlucky and we're in the firing line of one of these balls of plasma. And in doing so, it can induce electric currents in the electricity grid on Earth, which can be destructive to transformers and other electrical systems. So yeah, that's one of the risks. There's a variety of other things that can be damaged through space weather. It can affect satellites. The plasma balls can kind of induce electric currents in satellite technology, and there's also a whole load of charged particles that are sent out from the sun and during these explosive events that can cause a whole load of problems for satellites and aeroplanes. But the most interesting and most relevant things to the energy sector are these induced currents in the electricity network and damage to other electronic devices due to particles that are very energetic from the sun that can actually reach the ground level. And if you get one of these particles into your nuclear power station shutdown system, then we basically want to make sure that the system would be resilient to that kind of impact. And obviously, these events are not going to. I don't want to scare people that these events are not going to affect your health. There's no way in which you can be affected by these events directly like that. But since we're at EDF trying to manage very safety conscious and very critical infrastructure, then we need to be really on it with these very low probability but potentially high risk events. So yeah, I guess I was going to talk a little bit about the kind of perspective on the industrial side, which I think was quite interesting, at least to me when I first started this work. The nuclear industry is very much governed by its nuclear regulator. So this is in the UK, it's the Office for Nuclear Regulation. In France, it's the ASN, and they basically define the aims, the safety aims that nuclear power stations should all be trying to live up to. And they basically give out a variety of these very, very dry technical documents like the safety assessments principles. And these are long things that you don't really want to read, but they're kind of useful for us to have a benchmark through which to try and kind of get our safety levels up to. So that one of the main things that they push for is for us to have a designed-in resilience in all nuclear power stations up to a 1 in 10,000 year event for external hazards, which includes flooding, earthquakes, space weather, that kind of thing, and a 1 in 100,000 year event for man-made external hazards. So these are extremely unlikely events, but given the critical nature of the technology, there needs to be a very acute focus on safety and on these and estimating what these very extreme events would be. And yeah, so once we kind of have the input from the nuclear regulators, the aim really is to then try and build this hazard resilience in the nuclear power stations and other energy infrastructure. I'm not an engineer, so I don't actually do any of the building of any of these things, but I guess my job is more to try and aid the design of these structures by doing this sort of data analysis and trying to give the engineers and safety teams at each of these nuclear power stations an idea of what hazards are being posed to their systems that they're trying to manage. And I guess there's like 3 levels through which you could try and build a resilience in a system. The sort of worst approach would be to try and do this by trial and error, which would be like build your system, wait for something bad to happen, and then try and fix it and make sure it doesn't happen again. This is like the no-go zone for hazard resilience. The sort of amber level is trying to build in operational procedures at, say, nuclear power stations or whatever critical infrastructure you're trying to manage, which will be something like making sure that the people that run the systems know what to do in the event of a natural hazard, a flood, a space weather event, etc., so that they can sort of follow a series of steps to make sure that everything's safe and shut down in the appropriate way. And that's kind of like great if we can do that, and is an important part of the whole system resilience. But the main focus really is to try and get resilience by design, and this is the kind of the optimum that you want. Really, it basically just means you want your system to be resilient to all the natural hazards that you're interested in its design. So you don't need to have any people with a reams of documents to sort of follow if in the event of a hazard, of a catastrophic event, and instead the idea is that you want the system to be safe just by design. So even if no one, like, it's like passively safe, even in the event of a huge flood or a huge nuclear, a huge space weather event or that kind of thing. That's kind of the gold standard. That's why we put so much time into trying to estimate what these values of these extreme natural hazard events are. So back to space weather things. Maybe I'll skip through this because I think this will take a little bit too long to explain, and then I'll talk about what this is. So one of the key risks that space weather poses to nuclear power stations is through ground level enhancements, which is the name given to any particles that are accelerated from the sun. So when I say particles, I'm talking about subatomic particles. So protons, neutrons, electrons, and sometimes some heavier ions that are accelerated during these huge explosions on the sun, known as solar flares. And some of them get fired out into space. Some of them will interact with Earth, with the Earth's magnetic field. When they do interact with the Earth's magnetic field, if they haven't got that much energy, then the Earth's magnetic field will deflect them if they're a charged particle. But sometimes the particles have so much energy that they can be, even if they're deflected a small amount, they'll still end up interacting with the atmosphere of the Earth. And when that happens, you get what's called an atmospheric cascade, which is kind of summarized, I guess, in this picture here. So this is the Earth, an artist impression, and these are the incoming charged particles. And when they hit the atmosphere, you basically get this shower of collisions where these particles from the sun are colliding with particles in the Earth's atmosphere and basically leading to a shower of new particles that are being created and decaying and colliding, and there's a whole host of things that are happening with a variety of quite exotic particles. And some of those will can reach the ground level on Earth, and if you're particularly unlucky, then one of them can fire directly into an electronic device that you have. And in doing so, they can cause very localized errors in your electronic system. Sometimes they're called bit flips and this kind of thing, where you basically one of your ones will become a zero, one of your zeros becomes a one, and that can happen through a variety of different mechanisms. There are yes, some ways in which this could happen and it wouldn't really affect your system, but there are a small number of ways in which this could happen and could lead to a failure of some kind in your electronic system. And this could happen to any electronic device. but you probably shouldn't really worry so much about your phone and your laptop, because it's very, very unlikely that this kind of thing would happen. And if it does, then it's not the end of the world if your phone or your laptop gives you some erroneous reading or breaks for a while. Whereas when you're dealing with electronic systems at nuclear power stations that need to be always on hand if you need to shut down the power station or do some other crucial, like safety critical electronic implementation, then you really need to make sure that those systems are working all the time, even if there is a significant space weather event going on. So yeah, this ground level enhancement idea is one of the risks that we want to manage. And these happen about once per year, to give you an idea of frequency. And they're impossible to forecast because they just travel so fast through through space. So one of the tasks that we've done, well, this was a few years ago actually, but it kind of gives a good idea of implementing the extreme value analysis for an interesting hazard at nuclear power stations. So the aim with this is really to try and understand what the N year events are for ground level enhancements. So what's the sort of highest number of particles that are going to be interacting with any square unit area on Earth for a particular N year event. So the sort of crucial particle that we were modeling in this system was neutrons, which is one of the main particles that can reach ground level and cause these electronic problems. And we used data from a neutron monitor that's in Belgium. And you can see the data here. These are all the different times that neutrons were detected on the ground level that we think were generated from solar events. And this one here in red is the biggest one that was observed, which is much bigger than the rest. So the sort of key worry is that how much bigger can this kind of get? And the idea is to try and model these extremes using extreme value analysis in order to predict, to try and estimate that. So in this case, we used the threshold exceedances approach. So this was by selecting a threshold, we could then fit the generalized Pareto distribution to all the data points that lie above that threshold. And then, yeah, after a variety of kind of data science approaches and techniques, and trying to make sure that the fit of the distribution was stable and wasn't going to be perturbed if there was small changes in the data, then you can basically produce a hazard curve, which basically gives you an idea of what the severity of N-year events are. So this is very similar to that curve that I showed you before, which gives you, for each N-year event, it gives you an idea of what the severity of that event is, or what the return level, they call it, of that is. So all these points here correspond to each of these threshold exceedances that are above the red line. And then the black line is the kind of best Pareto fit to those values. And then using, I think we used a bootstrapping approach, we derived a 95% confidence interval, which is the dotted gray line. And in doing so, you basically can estimate what the severity of these N-year events is. But of course, as you can see here, like the error bounds tend to be extremely large when you're doing extrapolations out to a very long time into the future, to the point where you sort of tread this fine line between things even being believable at all, because after a certain point here, we're basically getting into territory where the statistical model is saying that there is quite a significant chance that the value could be negative. And of course, it's doing this because it doesn't know, the statistical model is just taking the data and trying to fit the model to it. it doesn't know that it's actually, it's of course impossible to get less than 0 neutrons interacting in per square centimeter on Earth. So there are kind of ways in which you have to interpret these estimates in the context of an understanding of the hazard and an understanding of like the other context involved. It's sort of one of many inputs that you should be using when you're trying to characterize these events. Okay, yeah, that's just a zoom in of the same plot. So for ground level enhancements in particular, we can use this this extreme value analysis approach, but we can also combine it with other methods, like I mentioned. So one of the additional measures that I think is really important for this hazard in particular is going into the history books and looking at, I guess, like paleoclimatology data. So basically, the extreme ground level enhancements, when you get all these neutrons that are hitting the ground due to solar storms, then they can end up being causing certain very unique ions to be created in the atmosphere, and then they can be they basically get trapped in things like ice cores and tree rings in a way that you can basically know exactly which year those ions were trapped in, because you can measure the age of the tree, you can measure the depth of the ice. And in doing so, there are some estimates of very extreme ground level enhancement events in the past, in like thousands of years ago. And we basically use these additional data sets of estimates, like very uncertain estimates, of course, but estimates nonetheless of very extreme events. And we can use them as well to supplement the more modern data, and to show that actually there can be some events that are just many times more severe than we've had in the recent history. And this is a very key part of the analysis that we do. Yeah, maybe I'll move on from that because I'm running out of time. And maybe I'll just leave a bit of a summary up for people to read. Yeah, so I've talked about the context of the nuclear industry and kind of why we're doing natural hazards research, what EDF is doing in that area, and in particular, just using extreme value analysis to forecast and sort of estimate what the severity of N-year events is for a variety of different natural hazards. The aim being to try and characterize what the 10,000-year events are, because then we can basically build and manage nuclear power stations in order to be protected from those extreme events across all the natural hazards that are relevant to that area. Yeah, in particular, we sort of do this hazard characterization in order to build in resilience into the design of these systems, as well as trying to make sure that the operators are kind of knowledgeable about what to do in an event. But the sort of gold standard really is to use all of this extreme value analysis and other tools to build in resilience into the nuclear power stations and make sure that they're protected now and in the many years to come. So I've probably overstayed my or overtalked my welcome now, so I'll leave it up to questions for the next 10 minutes if there are any. So thank you.
Great, thanks, Matt. And I'll clap on behalf of everybody else.
Thanks.
That was great, thank you. So have we got any questions? Feel free to pop them in the chat and I can unmute you. While people are thinking, I had a question and I had audio issues, so I'm sorry if you've answered this while I was cut out. But
No problem.
You mentioned about the extreme value theory. How much does global warming affect that? Because obviously the extremes are getting way more extreme.
Yeah. Yeah, so it depends. First, it depends what hazard you're interested in. So there are some hazards where global warming is not relevant, as in it doesn't affect them. So Space weather, for example, is not affected by global warming because it's like these events are basically it matters what's happening on the sun, not what's happening on the Earth. But of course, there are lots of hazards, especially coastal hazards in the UK and other parts of the world where, yeah, the climate change is really affecting that. If you're talking about sea level rise, talking about the greater extremes in flooding and all sorts of wind, all sorts of stuff. So you're right with that. So one of the assumptions in kind of vanilla level extreme value analysis is that the data is the distribution that the data is coming from is stationary. So this basically means that it's the same distribution throughout time. And each time you get an event, it's basically just plucked from that same distribution. That's what the assumption is. That's sometimes you can just get away with that and be like, yeah, this hazard is not related to climate change, so it's not going to change. So you can assume that it's stationary. But sometimes if you've got a data set from, I don't know, 2020 back to 1920 in sea level, then of course you can't just take that to be stationary. So there's a variety of different methods that people use in order to get back to something stationary. So people can detrend the data, that's one option, and then go ahead with simple extreme value analysis on that. But there's a whole load of other really in-depth or more in-depth, more sophisticated approaches where you can use non-stationary extreme value analysis, basically where you're fitting a distribution that has a time varying, or usually it's a time varying parameter. So say the shape parameter, for example, might be, or the location parameter could be time varying. So you'd have like a linear function or a quadratic function that gives you this varying parameter through time, and then you can use that more sophisticated model to fit to the data.
Great, thank you. That was very interesting. Do we have any more questions? Okay, so Demetrius has asked, do value at risk and or expected shortfall ever feature in your risk analysis, and ignore this if not?
Yeah, so I mean, I guess there's like different jargon for different sectors, isn't there? So I think those are kind of more like financy jargon, or at least that's where I've kind of come across those words. So yeah, there is. I'm trying to think of the kind of differences in the approach that are taken between the industries. Yeah, those phrases aren't really used in the nuclear energy industry for risk assessment, or at least not that I've come across. But there's probably like equivalent ideas. So there's like definitely a focus on prioritization of risk and R&D at different assets, depending on their like, I guess the value that is at risk, or the how susceptible different assets are to different hazards. Expected shortfall I've not actually come across, but I presume it was a finance thing as well. But yeah, I've probably not answered all that well. But yeah, I guess in short, that there are similar ideas discussed in risk research in the energy industry. But I guess like there are more discrete. I don't know, it's less continuous. There's more discrete things. It's like you don't have a portfolio of like many different investments that you have. Instead, you have like maybe 10 nuclear power stations, and like that's not going to change massively over time. And instead, you can think about what your prioritization for each natural hazard is across those, say, 10 nuclear power stations. Maybe some will be more susceptible to flooding on land from rivers. Some will be more susceptible to flooding at the coast. Some like. And yeah, the aim really is to do site-based analysis for the end year events to define the, say, 1,000-year event on site for each one, because it might be different in different places, and then build based on that site-specific analysis.